This is your brain. You use your brain for many things, coordinating your movement, allowing the processing and conversion of photons into an interpretable jumble of pixels that represents life, speaking to your neighbour about how blasting Def Leppard at maximum volume on their Focal Trio 6 BE active studio monitor speakers at 7:30 AM in the morning isn't really socially acceptable behaviour, and having a friendly conversation with your fellow peers about how League of Legends is an utterly diabolical game, and anyone that plays it either hasn't left their home in 6 years or uses 4chan. In summary, brains are pretty powerful. In the field of deep learning and artificial intelligence, the idea that we can copy biological concepts and represent these ideas in mathematical ways has been a monumental catalyst for the creation and development of computer algorithms that display intelligent behaviour far beyond the capacity of the human brain. Neural networks are a prime example of the inherently narcissistic idea that the human brain is good at challenges requiring non-linear solutions. In this video, I am going to discuss the main components of one of the many types of neural networks that is in existence today, the feed-forward neural network. What is a feed-forward neural network and how does it work? In a simple sense, it's a distribution of functions that when passing in an input, returns a result after a mathematical calculation. The complexity of the neural network is dictated by a number of hyperparameters: the amount of hidden layers, the amount of nodes on each layer, and the activation functions used. Now, if you have no idea what any of these things mean, then have no fear, because we're about to discuss them now. Right, starting from the very beginning. First, we have our input layer. To make it even simpler, we'll start off with a neural network with one input, one hidden node, and one output. On the very first layer, the input layer, we pass in our input. This number is then multiplied by a weight connecting the input node to the hidden node. The use of the adjective hidden merely means that the person applying the use of the neural network does not need to know the value of it. E.g., it is hidden within the black box of the math. After multiplying the input by the weight, we then add a bias to the value of this result. The weights and the biases of the neural network are initialized at the very beginning before we have passed in any inputs. For the purpose of this example, they are all randomly generated. To help visualize the math that is being performed from the input to the hidden node, imagine the input as x, and the weight as m, and the bias as c. First, as aforementioned, we multiply the x and the m, the input and the weight, and then add the bias. The equation of the input to the node is hence mx adds c. Now, anyone who has taken up to middle school math will realise that this is the equation of a linear line. As I explained earlier, a neural network is merely a set of functions. However, we are not done with the math. The equation of mx adds c is, as I said before, the equation of a line. However, if we only ever apply linear mathematical equations to the inputs, then we will only ever receive linear outputs. This is an issue for a number of reasons, as most challenges that we'll apply neural networks to require non-linear solutions. To overcome this, we will use what is called an activation function. Activation functions are used to add non-linear behaviour into otherwise linear mathematical equations. Quite simply, we pass the value of the weight times the input, add the bias, into this activation function. Currently, in deep learning and the ML communities, there are lots of different activation functions used, although some of the most popular include the tanh, logistics functions, also known as sigmoid, and ReLU. Each different activation function has different behaviours and attributes that are subjectively used on different applications. For the purpose of this video, I will be using the sigmoid function. So after we've passed the value of mx adds c into our activation function, we repeat the previous steps, only with the output of the activation function as our new input. The way our inputs forward propagate their way through the network is precisely the reason the neural network is named as it is. After we have done this for all of our nodes and our layers, we have our output. So to reiterate, we take our input, multiply it by a weight, add a bias, and feed it into an activation function. That's all it is. But wait, surely a neural network with lots of inputs and lots of hidden layers is a lot more complex? Well, no, not particularly. Instead of just adding one input times weight into our node, we put the summation of all the inputs times their corresponding weight connection into the node. And then we just add the bias like normal and pass it into the activation function. At this point, we have basically finished all of the math behind the neural network. We can now just stack more nodes and more hidden layers into our neural network, and the mathematical processes stay the same. In reality, there are lots of other considerations we have to make when implementing neural networks. Number 1. Is this the correct neural network topology/type for the task at hand? E.g., feed-forward neural networks are usually okay for math that involves continuous data. However, when we're dealing with sequential data, we might be better off using recurrent neural networks, or an LSTM. Both of these I want to make a video on at some point. In addition, if we are working on something like an image classifier or a chatbot, we may need a convolutional neural network or a transformer. No, not a big metal clanky boy. A mathematical model that is showing great potential for a large amount of issues that are being tackled today in the AI space. Surely we are done now, right? Right? Well, yes, but actually no. The basis for our mathematical model to compute our inputs and return our outputs is done. But how does it learn? How does it know what weights and biases it should use for the neural network? There are many ways it can do this, but in deep learning there are 3 categories for which learning algorithms can be categorized. Number 1, supervised, unsupervised, and reinforcement learning. The most common supervised learning algorithm is called backpropagation. I will not get into the math of this in this video, but in its rawest form, it's updating the weights and biases of the network, depending on how close the output was to the desired output. Another very common algorithm used in reinforcement learning is a genetic algorithm. If you want to find out more about how this works and how it can be used to make your AIs learn, check out my video on screen now. Thank you so much for watching this video, guys. I hope you all enjoyed it and found it educational. If you have any tips for how you think I could improve my content, drop them in the comments down below and I'll be sure to respond. As always,